my shirt? Yeah.
Anti-reflective coating for a camera lens.
Never mind.
The lens itself is made of glass, and the coating material will have an index of refraction of n equals 1.35. Okay? What is the minimum coating thickness that would prevent reflection of light whose wavelength in vacuum is lambda 0 equals 500 nanometers? Note, for this part of the problem, assume that the light enters at normal incidence, which is perpendicular. Okay, everybody follow? All right. So, third piece of railroad chalk. In air, bouncing off of 1.35. Flip or no flip? Flip. At the bottom, in 1.35, bouncing off of 1.5. Flip or no flip? Flip. Therefore, if I did nothing else but flip them both, constructive or destructive? Constructive. So therefore, the 0 lambda goes with constructive. Meaning that, so does the 1 lambda, 2 lambda, 3 lambda. And destructive occurs if you slide these two waves by half lambda, 1.5, 5 half, 7 half. Agreed? Everybody with me? Now, what are we attempting? We want to make an anti-reflective coating. Anti-reflective means that we're interested in what kind of interference? Destructive interference. To make an anti-reflective, we want to kill the reflection. And how do we get destructive interference? What's the thinnest film that would do that? Half lambda. So, the thickness of the film is D. The distance I go is how much compared to D? 2D, because I've got to go down and back. And according to this, to get destructive, I want it half lambda. Now, should that be lambda 0 over 1, lambda 0 over 1.35, or lambda 0 over 1.5? 1.35. The reason is that while you are in this medium of D, that's when you're in the index of refraction of 1.35. So twice D should be this, which is half lambda 0 over 1.35.
D3.
Okay? What do you think? Reasonable?
Yep.
How much did you come up with for D?
93 nanometers.
Is that possible? Can you make something only 93 nanometers thick?
We're trying.
No.
How does it compare to the size of an atom? How big is an atom? Yeah. I heard somebody say it out loud.
I'll look it up.
An angstrom, yeah.
What?
Most atoms are about the size of an angstrom. So, an angstrom is a tenth of a nanometer. 93 nanometer coating would be about 930 atoms thick. Sure, no problem at all. This is reasonable. Okay?
Is it possible, though?
What?
Is it possible?
Oh, sure.
So the order of magnitude for the magnitude, negative magnitude, an angstrom?
No, angstrom is 10 to the minus 10.
Okay.
And it fits outside of the milli, micro, nano, pico because it's special. And that's the easiest way to remember that an atom is about an angstrom. Now, if you ask me, do I mean diameter or do I mean radius? The answer is yes. Because about an angstrom, okay? Not 1.000 angstroms, but about an angstrom. So, do I mean diameter or radius? Yeah. I mean diameter or radius or thereabouts. Roughly an angstrom. So, when you look at something that's 93 nanometers, that's 930 angstroms, that's 930 monolayers. In fact, that's really thick for silicon circuitry that you would use in the chips in your devices. Okay? That's more like a coating we put on the lens. Oh. What do you know? Okay. So, move down a little bit, and here's part B. Now, in part B, what we're going to do is we're going to bring in the light at a grazing angle. Okay? And in this case, we're not going to calculate any interference at all. We're just going to consider light that goes bent down to the bottom, reflects, and comes back out. And what we would like to know is the distance between where it entered and where it exited. What kind of a problem is this? Snell's law. Don't worry about flips. Don't worry about phases. Don't worry about blah, blah, blah. This is just a Snell's law because you need to do a little bit of geometry. Okay?
Yeah.
N1 is 9 theta, that's 2 9 theta.
Yep. The chalk is interesting. No, I'm serious. If you look at the outside of the chalk, you can see that there's a little bit of a coloration to it. But once you get in, you can see that it's pure white. The chalk is covered with a very thin plastic coating to keep dust off of your hands for the most part. Most people who use that chalk don't know. So this is the chalk that somebody else left behind. What you can see is that they used it from both ends, which means the part that comes right off in your hands as soon as you touch it is exposed at both ends. So this kind of chalk, you hold it from one end and you write with the other end. And the first time you break through the plastic, it doesn't write for a moment. And so you don't get a line, and it looks a little bit of yellowish. And then after that, it writes fine. All right. Yes, that's on the test.
Extra credit.
Extra credit?
Yeah.
How many sticks of chalk you went through in your review? 3.
Is it really?
Is it really 3?
Okay.
How many sticks of chalk that you went through in this review alone?
I think this is the third.
Oh. Remember, the answer is 3.
I think this is the first. No, that's the second. This is the first. You can tell it's me because it's still square on the bottom. And
2.5.
this was the second, but it started to get too small to hold, so I went to 3. All right. Now, we're asked for this distance. However, what I claim is that's twice as much work as we actually need to do.
Should figure out head space.
Yes. If we simply figure out
And then times it by 2.
this distance here, and then
Double it.
We're done. Agreed?
Yep.
What? What's the rule of reflection?
It's the same.
Angle of incidence equals angle of reflection. So that's it. It has to be, it has to be, what's that phrase? Blank symmetric? Has to be mirror symmetric.
Oh.
Because at the bottom it's a mirror. Yeah. Okay. So in that case, this is theta 1. Were we given a theta 1?
Mm-hmm.
Theta 1 is 50 degrees. So 1 sine 50 is what? Is what? So what's theta 2? Okay? So, are we supposed to use the thickness? Oh, using the thickness determined in part A. So that was, what, 94 nanometers? So that's 93 nanometers. Is here. Let's call that little distance, so let's not call it D. Let's call it XO2.
XO2, yeah.
Okay? Good name. So then, how is theta 2 in here related to those things?
Tangent, yeah, opposite of
So that gives me X.
128. 128 nanometers.
128. Ta-da! Not very far apart.
What does that say?
128 nanometers, nm. And no, even if you're live, you can't read it. It's a handwriting issue, not a
it is the board.
not a video reproduction.
128 nanometers.
Okay, so what do you think? Reasonable?
Reasonable.
It's a thin film followed by a Snell's law. All in one. Okay.
No, I think I missed it. And I had to
Yay!
It's so scary.
Wrong zombie.
Yes, the class turned into zombies as soon as this appeared on the board, because immediately the room filled with. Now, the key to this problem is to be able to set the difference in the paths related to the appropriate number of wavelengths. Okay? You have 2 point sources separated by D. And you look out here at an angle theta. The far field approximation allows this to be perpendicular, so that that side there, we have recently started calling that delta, is equal to what?
X sine theta.
D sine theta. When we're taking a large collection of many such points, each of one has a different x, we were calling that x sine theta when we were taking the Fourier transforms of these. Now I'm calling it d sine theta because I've only got the 2 points for the 2 squares. Everybody with me? Okay? Now, d sine theta. Oh, as light passes through an opening, ta-da! Does it flip or not? Not. So there's no flips in this problem. Meaning that how do I get constructed? D sine theta equals what? 0 lambda or
1 lambda,
1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6 lambda, etc. Everybody with me? Now, each feature in the diffraction pattern can be identified with one of those possibilities. Right there's the middle.